Now, so you have the fibers, and you're going to put the fibers inside the matrix. Now, I want to show you some examples of ceramic matrix composites. And when you talk to somebody working in composites, that person will tell you that the interfaces are probably the most important aspect of a composite. Now, the interface is the region between the fibers and the matrix. So if you're going to be making an airplane, and I'm going to show you an example of how Boeing uses this type of materials to make the 787 or some military aircraft, these components are subjected to large mechanical stresses. So the stresses are first applied to the matrix, and then the matrix transfers those stresses to the fibers. And that transfer of stress happens at the interface. So in the case of polymer matrix composites, and also in the case of metal matrix composites, you want very strong interfaces. You want the fibers to be almost perfectly bonded to matrices. And this is why we use things like epoxy. You know, epoxy is an adhesive. It's a glue. And this is the reason why epoxy is such a good material to make this type of composites, because it attaches, it can bond very well to the fibers. Now, sometimes it's difficult to bond to carbon fibers. Did you remember that video of pan? They have this constant stretching. What happens when you are stretching these molecules? What do you think is going to happen? Have you heard about texture? So if you have a metal and you have a chunk of metal and you pass it through rollers, what happens to the crystalline planes? They get aligned, okay? And that's what we call texture. You have a crystallographic alignment. And the same thing happens with these carbon fibers. In the case of carbon, what you have so you have carbon, okay? And these are what we call the basal planes of graphite. So graphite is made by having many of these planes stacked one on top of each other, okay? So we call these the basal planes. Now, between the planes, they are connected by van der Waals forces. These are very weak forces. But on the plane, these are very strong covalent forces that keep the carbon together. If you stretch your precursor, your pan precursor, during this process of constant stretching, these planes are going to tend to align along the length of the fiber. So on the surface of the fiber, you're going to have these basal planes. And sometimes it's very difficult to attach, to glue to these first, which means that you have to do something to the surface of the fibers. And that's what we call functionalization. So I'm going to show you an example of how we have used some treatments to modify the surface of fibers in order to improve the interfacial properties.
During the microwave-assisted plasma or MAP conversion process, crimped or spooled pan fiber feeds into the pre-treatment module and proceeds through a steam heating and stretching process. The fiber enters an atmospheric pressure plasma oxidation module, darkening from white to black as it weaves through the first of several oxidation ovens. The number of ovens can vary based on production needs. Inside, the atmosphere is controlled and air temperature is lower than with conventional processing. The special chemistry of the atmosphere accelerates oxidation. The fiber then enters the carbonization phase. Microwaves and plasma provide the energy needed for carbonization. Approximately half the material is vaporized, with gases exhausted through an incineration system that is much smaller, less expensive, and requires less energy than conventional processing systems. The remaining material is nearly 100% pure carbon as it enters a surface treatment process that renders it chemically compatible with resin. Surface treatment occurs inherently near the exit of the MAP carbonization module, thus eliminating the need for a separate surface treatment module. A thin coat of polymer is applied to the carbon during sizing, which protects the fiber and makes it easier to handle. The carbon fiber is then dried and packaged, typically by spooling. Experimental data from laboratory-scale experiments suggests that microwave-assisted plasma conversion takes approximately 1/3 of the time and 1/2 the energy required for conventional processing.
So here is a, yeah. ¿Sí van siguiendo la historia? ¿Sí? Yeah, in the case of the automobile, absolutely. You know, a lot of times the let me tell you about. I'm gonna go around to answer the question. And when I got my PhD was sponsored by the Office of Naval Research, and there is an agency called DARPA. Have you heard about DARPA? The Defense Advanced Research Projects Agency. DARPA is an organization which is part of the Department of Defense. And DARPA was created in the late 1950s by President Eisenhower. When the Russians launched Sputnik, Eisenhower said, we cannot afford to stay behind the Soviets. And the charge to DARPA was to develop any technology possible so that we will never be surprised by a Soviet satellite going around the air. People were really scared at the time. So DARPA became a very aggressive program, and any proposal that was funded by DARPA had to be something very ambitious. If it was easy to make, DARPA said, forget about it, somebody else can do that. DARPA is responsible for the internet, okay? In fact, the first two computers that talked to each other was a project funded by DARPA. And then DARPA established something called the ARPANET. This is the first computer internet. And the internet that we know as the web today is actually derived from the ARPANET. So this agency, I mean, think about the implications of the internet. I mean, we have revolutionized mankind with the internet. So that came from DARPA. Today, soldiers coming from Afghanistan and Iraq who have lost limbs, they have now prostheses that can be controlled by the brain. And that's something that DARPA developed. And what DARPA was doing, you know, one of the big concerns that if there was a nuclear war, the pilots will have to fly into Soviet space. We had missiles and the missiles, but the idea was that you wanted to surprise people with your bombers. And the problem is that if you drop the bombs in the Soviet Union and the bombs explode, there was a risk that the pilots will not be able to make it back. So they started looking at remote control of aircraft, where you will be sitting somewhere in Houston, and with a joystick, you know, you'll be controlling remotely. And as a result of that, they were able to develop brain interfaces. I mean, you had people sitting, and then just with their thoughts, they were able to operate instruments. And as a result of that research, what you have now is you have these artificial prostheses that they attach to soldiers who lost arms or legs, and they connect them to the brain. So now you say, I want to move my arm, and then you move the arm. I want to grab that object, you grab that object. You know, in the old days, there was very little mobility, but now everything's controlled by the brain. All that research was funded by DARPA. So, you know, there's always a criticism of the US that, oh, you guys spend so much on military, blah, blah, which is true. But when you look at the implications of those investments, there's always something good that's going to come out of that. So the question that you ask is, okay, you know, it takes so much energy, and these fibers could be better than steel, but at the end of the day, may not be good enough. Well, for military applications, DARPA funded a lot of work in composites. And they say, you know, we know this is going to be 20 times more expensive than steel or aluminum. It's going to take 10 times more energy to make them. But at the end of the day, the final product is going to make a better military aircraft, and we're going to beat the Soviets. And as long as you gave yourself an edge, it didn't matter how much it costed. You know, they knew that 20, 30 years down the road, the technology would probably become affordable, and then people would use it. But the immediate application of the technology was military applications. And so what we have seen in the case of composites is a good example. Now, the reason why I mentioned this is that my research, when I did my PhD, was funded by DARPA. And we were looking at ceramic matrix composites. So on Thursday, when we talk about gas turbines, I'm going to give you examples of how we use ceramic matrix composites to improve the efficiency of engines. First, for military applications. But now this year, General Electric just announced that there's going to be an engine flying on the 737, on the Boeing 737, that uses these materials. And by doing that, you can make the engine much more fuel efficient. So you can drive longer distances with less fuel. It's going to be less expensive to operate. You know, it took almost 30 years to translate the research from the military space to the civilian space. But these are the consequences. So early on, you're right, the cost is very high. The benefits are there. You know, if you have a lighter aircraft, it's better. More powerful engine is better. It may take a few years before you can introduce that into the market, but it's just a matter of time. And the same is true with carbon fibers. You know, it's very expensive, but if you, and I don't have a plot showing cost versus time, but you know, in the last 30 years, the cost of carbon fibers has really plummeted. I mean, it was only the military that could afford to do this. Nowadays, you know, you're going to find them more and more in automobiles and other applications. The other message from this last video is that by using this assisted plasma process, you can reduce the energy intensity of the process. You have actually reduced the amount of energy that you take to make the fibers. So this is how, you know, this is how technology works. You know, people are always looking at, you know, can we do something to reduce the energy intensity? Can we do something to reduce the cost of the precursors? And so forth. So that's part of the process. Okay, make sense? Okay, ready? Okay, very good. Okay, so let's continue. Any questions about carbon fibers? No? Again, the main reason for looking at carbon fibers is that table I showed you that shows the specific properties. When you normalize by density, nothing gets anywhere close to carbon fibers, okay? Nothing, absolutely nothing. Carbon fibers is one. Now, there is I was talking with Jose Ignacio, and he mentioned that they had organized an event not long ago talking about graphene and carbon nanotubes. These things are related. If you think about it, a carbon fiber may have 5 microns in diameter, but a lot of these fibers have an onion skin type of a structure where you have layers. And what you have in these carbon fibers are layers of graphene, just one on top of each other. When you pull the fiber, it's very stiff, very strong, because you are actually pulling against these carbon-to-carbon bonds. The fibers may be put in shear. You know, have you seen these telescopic lenses that you can actually have a cylinder and then you can extrude the cylinder? That's what happens with these carbon fibers. That property in shear is very low because it's just constrained by van der Waals forces. But when you hear about carbon nanotubes, when you hear about graphene, that's what these fibers are all about, except that you have many layers of graphene or many carbon nanotubes surrounding one around the other, okay? It's the same idea. And this is why these fibers are so stiff, why these fibers are so strong. And the reason why carbon nanotubes are even stronger is because of Weibull size effect. The smaller the object, the less likely it is to find a defect. This is why the strength of carbon nanotubes is just so astronomical. That if you have a perfect carbon nanotube, I mean, the strength can be, you know, 100 GPa of a strength, I mean, which is, just think about the, it's an astronomical number. So. Okay. So let's talk about ceramic matrix composites for a minute. We talk about the interface, and I show you an example of how using plasma-assisted processes, we were able to reduce the energy intensity of the process, okay? But the other advantage of using plasma is that we were able to modify the surface of the fibers. In the case of polymer matrix composites, we want a very strong interface between the fibers and the matrix, okay? In the case of metal matrix composites, we want a very strong interface between the fibers and the matrix. In the case of ceramic matrix composites, we don't want a strong interface. We want a relatively weak interface. We want an interface that's going to be strong enough to transfer load, but weak enough to deflect cracks that may occur in the matrix, okay? So in the case of ceramic matrix composites, the paradigm is a little bit different. You want a weak interface, which may be counterintuitive, but that's what gives these materials its tough behavior, okay? So let me ask you a question. Let's assume that we want to make a ceramic matrix composite, okay? And we want this composite to be strong, and we also want that composite to be tough. Okay, and by tough, we mean we want a material that will absorb a lot of energy before it fails. Okay? So we want to make a composite, a ceramic matrix composite, reinforced with fibers, but we want it to be strong. It takes a lot of stress before it breaks. And we want it to be tough. It means that it absorbs a lot of energy before it fails. Okay? So if I pull a metal in tension, and I'm going to plot stress versus strain, and I have a piece of metal, and I'm going to pull it in tension. What does the stress-strain curve look like? Go up, okay, and then yields, okay? That's what a metal stress-strain curve looks like, okay? What's the slope of this curve? Modulus, very good. And then if we have an offset, let's say 0.05%, we have what? The yield strength, okay? We have necking here, and then the material breaks. And then if we have this area, what is this area? What does this area represent? Toughness, okay? In fact, it has units of energy. So the area under this curve is the energy that the material absorbs before it breaks. So it's a measure of toughness, okay? The greater the surface area under the curve, the tougher the material is going to be. So to have a tough material, you want to have high strength and then a lot of ductility. If you take a ceramic, a monolithic ceramic, you pull it in tension, what do you get? And then breaks, okay? So when you compare the surface area of this versus this, it doesn't compare. Even though this value may be greater than this value, the surface area that you get under the curve is just a small fraction what you get with a metal, okay? Brittle behavior, tough behavior, okay? So in the case of ceramic matrix composites, I want you to think about this. You have ceramic fibers. So if I take a single fiber and I pull this fiber in tension, this single fiber is going to behave like that, okay? But now I'm going to take 100 fibers or 1,000 fibers, and I'm going to make a composite. And then the question is, how is that composite going to behave? I want that composite to be strong, to have high tensile strength, but I also want that composite to be tough. How do I make a composite that has high strength and high toughness, just like a metal, okay? And I want this to be a ceramic matrix composite. So each fiber in the composite is going to behave like this. So the question that I have is, can I really make a material that will behave like this, where the constituents behave like that? What do you guys think? Is that possible? You know, intuitively, it says, no, you know, if I have a bunch of fibers and each fiber behaves like this, and the matrix behaves like this, how can I have something that in combination can behave like that? That's a tough one, isn't it? Okay, so let me show you a little exercise. So we're gonna do an exercise. And then the other question is, these fibers that I'm gonna use have a Weibull, the strength of these fibers can be described using a Weibull distribution. And we just saw a Weibull distribution a minute ago, okay? So the question I have is, do I want fibers with a small Weibull modulus or with a large Weibull modulus? Okay? Small, okay. Anybody high? No? Everybody small? Okay, well, you guys know the answer already. So let's do a little experiment. So we're going to go to the lab. Have you guys been to the mechanical properties lab? So you have an instrument machine or an MTS machine. So those machines have a load cell. So the load cell is a transducer that gives you the force. You can measure the force with the load cell. And over here, we're going to have the crosshead of the machine. And we're going to program the machine to move at a constant speed. Okay? And then I'm going to attach a bunch of fibers. 100 fibers, 1,000 fibers. And these fibers are perfectly aligned. And I'm going to glue all the fibers on the top, and I'm going to glue all the fibers on the bottom. They have the same length. I grab them on the bottom. I grab them on the top. I connect the top to the load cell. I connect the bottom to the crosshead of the machine. And then I'm going to move the machine at a constant speed. Now, before I do this experiment, I'm going to pick up a few fibers from the bundle, and I'm going to test them individually. Okay? And when I test those fibers individually, they're going to behave just like this, each fiber. Okay? Now, because these fibers obey a wobble distribution, I'm going to go and test my fibers. So I have stress strain, and this is the first fiber, okay? And then I test another fiber. It's a little bit stronger. Then I test another fiber, and it's weaker. Then I test another fiber, and it's right here and right here. So this variability is given by what? Weibull modulus. Very good. So the Weibull modulus is going to tell us how much variability do we have, okay? And then there's going to be a value of the characteristic strength that's going to tell us more or less where we are. Not the average, but is the equivalent of the average in these fibers, okay? So I'm going to test a lot of fibers, and after testing my fibers, I'm going to find the Weibull modulus and the characteristic strength. And I'm going to show you here in a minute how we do that, okay? So I test my fibers, I find this value, and then I go and I pick up more fibers from the bundle, and I mount them in my machine just like that. Okay? Are you guys with me? So now we're going to go and push the start button in the machine. And we're going to start, we're going to send the data to a chart recorder. Now the load cell measures force, okay? And we're going to define something called the bundle strength, or the bundle stress. And the bundle stress is going to be the force measured by the machine with the load cell. And then I'm going to divide it by the number of fibers that I have in the bundle. And I'm going to multiply that by the cross-sectional area of the fibers. So I go to the microscope and I measure the cross-sectional area of one fiber. And then I multiply it by how many fibers I have in the bundle, okay? And then I'm going to plot here the ratio of the force measured by the load cell divided by this number. And then in the horizontal axis, I'm going to measure the strain. Got it? So we send this to the chart recorder, to the computer. And there it goes. We start pulling, and you can see the stress. And now the fibers start to break. And they break at different loads because they obey a Weibull distribution. Okay? So what did we find? Number one, we find that the collective behavior of the bundle resembles that of a metal. Okay? Now, we did this experiment at a constant speed. So we were moving at a constant speed. But the collective behavior of the bundle looks like that of a metal. Okay? These are individual fibers being stretched. Each fiber follows a stress-strain curve that looks like that, just a straight line. The beauty of this is that the collective behavior that you have from a bundle of fibers resembles the behavior of a metal. Now, the question that I had for you was, do you want a high Weibull modulus or a low one? And you guys said low. So in this chart, I'm comparing what these stress-strain curves look like for different values of Weibull modulus. So if you have a Weibull modulus of 2, see how much ductility you get in the system. As you increase Weibull modulus, the distribution narrows down, the curves become much more deterministic, but also the strength of the bundle increases, okay? And this is really the reason why ceramic matrix composites are tough. it really depends on the stochastic nature of the strength of the fibers. If all the fibers broke at the same load, the composite will behave just like a ceramic. The fact that the fibers break at different loads, the fact that the strength of the fibers follows a wobble distribution, is the reason why we can have tough behavior in ceramic matrix composites. Okay? Now, why is this important? Well, this is important because if you are making a jet engine with a ceramic matrix composite, something that happens very frequently is something called foreign object damage, where you have birds getting into the engine, and a bird can destroy an engine. Did you hear that story of a captain that landed on the Hudson? No, it's about 3 years ago. It was a US Air flight, took off from LaGuardia Airport in New York, and as it was climbing, 2 birds, one hit each engine in the plane, so the plane lost both engines and had no power, so the captain made a U-turn, and it landed on the Hudson River. Okay, nobody died. I mean, it was an incredible story. But this is what happens when you have objects hitting your gas turbines. You can destroy the engine. So in the case of ceramics, if you put a brittle ceramic component, this is what's going to happen. If you have a ceramic matrix composite, this is what's going to happen. You are going to have something called graceful mode of failure. Okay, it's not a brittle mode of failure; it's a graceful mode of failure. And again, the area under the curve is going to give you a measure of how much energy the material can absorb before it fails. And this is one of the major considerations. Before you can put something in an engine, you got to make sure that it's not going to shatter into 1,000 pieces. It may crack, but still be held in one piece by the fibers. Okay? So this is the secret behind ceramic matrix composite. The reason why ceramic matrix composite can be tough is because you have a stochastic distribution of strengths in the fibers. Okay? Now, if you glue the fibers to the matrix very strongly, you're going to have this type of behavior. The first time a crack propagates to the matrix, it's going to break every fiber. If you allow the fibers to debond from the matrix whenever a crack approaches, then you're going to have this behavior. The fibers are going to be able to debond and slide frictionally in the matrix and be able to carry load. And they may break, but then the fibers can get reloaded and show this type of behavior. Okay? That's the secret behind ceramic matrix composites. The fibers are brittle. The matrix are brittle. The combination of brittle with brittle plus some interfaces will give you tough behavior. Okay? And this is really the interest in using these materials. They are ceramic, so they can operate at high temperatures. And now we have shown a way to develop materials that are tough, that can absorb a lot of energy for a specific engineering application. Okay, questions? Is that clear? Good? Okay. So the answer is we want strong fibers with low wobble modulus, okay? That's what's going to give you the toughness. Low wobble modulus, but you want strong fibers to do this.